So welcome everybody. The topic I'm going to discuss today, so molecular dynamics, is something which I realize is not very central to the themes of the historic MOMAS GDR. But it's something which came up in the last years, I would say. So my aim this morning is to present you, really to introduce you to this field of research. And I do not assume that you have any previous knowledge of stochastic differential equations and so on. So I will be very basic. I'll really guide you through an introduction to that domain. And also I'll give you lots of references if you want to know more. So if you get bored at some point, just tell me. But I mean, the point would be that you are, that the pace of the talk is really sufficiently slow so that you can follow up everything and that hopefully you understand even the last slides. Well, that would be a dream, but I mean, if you understand, I would say, until here, it would be already very good. So I'll present you briefly what statistical physics is about. I'm not completely sure that everyone is well aware of statistical physics and especially computational statistical physics. And then I will show you how to compute average properties of material described at the atomistic scale. And for the GDR, and I mean that's especially this last part, one important application of statistical physics is the computation of transport coefficients, such as the self-diffusion of ions in a solvent, say some charged ions between clays. That would be a typical method to do that, would be typically this kind of computation of transport coefficient methods, which is routinely done at PEXA, for instance. So really the aim will be to present you how to do that. And what does it mean? So I'll hand out the slides, so I mean you don't have to note down everything, but I like to start with lots of references if you want to enter the field. So there are theoretical statistical physics books, which are nice because everything is closed formulas and so on, but it's not computationally clear how to do that. If you want to have some computational method, you can look at several books in the physics literature, which are very nice to enter the field when you want to do something in practice. But the mathematical understanding behind the methods presented in those books is sometimes, well, a little bit scarce, I would say. So that's why I provide a next slide, which are some mathematical references. So there are lots of references about integrating the Hamiltonian dynamics, which I will not be so much talking about today. And so this is by now very well covered. And about sampling the canonical ensemble, which will be the focus today, I mean, the literature is less well developed, but there are some references which start to appear. So, for instance, those two books, one of them being a shameless advertisement to some work we did. Okay, so let's start with some elements of statistical physics. The first point is to give you some orders of magnitude, which are very, very, very different from the typical macroscopic orders of magnitude. And there is no way I can sufficiently emphasize that. So the first point is that the distances are the typical interatomic distances. It's of the order of an angstrom, so 10 to the minus 10 meters. The energies are very small. I mean, per degrees of freedom is something like 10 to the minus 21 joules. The masses of the particles are very small. It's of the order of 10 to the minus 26 kilograms. And the typical times are also very small. Here, in fact, I put the time, well, that's the typical time of a bond vibration in a molecule. So you see it's 10 to the minus 15 seconds, and if you want to resolve every bond vibration and integrate in time, you'll have to do a certain number of time steps before you reach something of the order of a second, not to speak of something of the order of 100 years, which is what Andra would like to know, what happens with the ions over very long geological times. So here you can already see that there is a challenge, and there will remain a challenge even in decades, about going from very small atomistic timescales to geological timescales, like kilometers and hundreds of years or even more. And also there is a challenge in the number of particles involved, because in some macroscopic piece of matter, like this laser pointer, there are about 10 to the 23 particles. Well, a bit more than that, but I mean, that's the order of magnitude. That's really a huge number. And to give you a feeling of how huge that number is, I can tell you that on Earth, there are 10 to the 22 moles of water. That's, so I mean, and molecular simulation will be simulating 10 to the 6, would say, particles instead of 10 to the 23. So the analogy would be, it's like inferring more or less what happens in a bathtub or in a pond, well, simulating a bathtub or a pond and then inferring oceans dynamics from that. So you see, it seems hopeless a task from the very beginning, but it turns out that in some cases, the easy cases, there is something that can be done already, that can be said already from simulating a pond with respect to oceans dynamics. But not everything, of course. So I mean, that's really a major message is that the timescales are very different from macroscopic timescales, and there is really a computational challenge here, and also a theoretical challenge. So what are the aims of molecular simulation? Know that you know that it's a desperate task. So there are two things we want to do. First thing is we want to, I mean, maybe I should start with this one. The first thing is that we want to have some macroscopic properties coming out of our atomistic models, which means that if I give myself some interaction rules between the atoms at the microscopic level, I would like to know what is like the average pressure in my fluid, or what is the stress-strain relation in my solid, what is the heat capacity, the thermal conductivity, and so on and so forth. So all kind of constitutive equations or thermodynamic coefficients can be inferred from some very detailed physics and very fine, I would say, fine-scale physics. So it's a way of putting the modeling effort into really the fundamental laws of physics, and then just taking out what are the macroscopic models coming. So that's the first aim, computing average property, and there is also a more, another aim, which is a numerical microscope, in the sense that you take your system, you postulate some interaction law, you simulate it on a computer, and then you look at the movie, and you just look at what's happening. So it's very easy to look at movies on a computer, because then you can see every atom move, and you can see very precise motions, which you cannot with typical experiments. On the other hand, it's not something which is, I mean, it's not really a real experiment, so what you see on a computer is not necessarily what happens in real life, but at least it can help you, give you some intuition, feeling, well, information about what could really be happening in real life. So it's really to have some ideas about what to look for in experiments. So this numerical microscope is something which is more and more used, especially in biology, well, to have some ideas about what's happening in complex systems. I wouldn't say, well, for me, I won't advertise it as an aim today. I will really concentrate on the computation of average properties. And so last point is, now that you know the actual orders of magnitude, what are the aims? Now what can we really do in practice? Is that we can simulate something like 10 to the 6, 10 to the 9 particles, and integrate that over something which is of the order of a nanosecond, maybe a microsecond if you really have lots of computers. So it's really, I mean, it's really about how to, since you can do that, how can you go back to that? So maybe some examples. So first, very simple example is the argon, argon. So in some conditions, when temperature is sufficiently high and pressure is well, sufficiently high as well, you can have a fluid. So atoms, so it's a disordered structure. You've got atoms which are close together. And when you're at very low temperatures, then the argon becomes a crystal, and the atoms are very well ordered. And so, for instance, you would like to know what is the melting temperature. So at which temperature you stop having such an ordered structure, and you go to some disordered structure. Another information you would like to have, for instance, is what is the equation of state. So what is the pressure as a function of the density for this fluid. So here is so my aim today will be to tell you how I obtained those little crosses, which are computations which I quietly did on my laptop computer. So you see the solid line here is some experimental data from the National Institute of Standards in the United States. So something which is really a reference, macroscopic thermodynamic measurement. So what you see is that for this very simple example, what I compute using the laws of statistical physics agrees very well with macroscopic experiments. And, well, there is one thing to note is that I can access to a very high pressure regime on my computer, which experimentally is very difficult. So this is a typical, I mean, maybe a too nice an example of a situation when molecular simulation on a computer can give you access to some information at a much, at a cost which is way below the actual cost of experiments. So and in this case, it's really something which is quantitatively predictive. So that would be the graal of all kind of molecular simulation, is to have something which is somewhat predictive from using some ab initio information without experiment. Well, of course, in real life, it's not always that easy, but at least it's a motivating example here. And on the right, there is here I make a zoom of that first part to show you that in the low pressure, low density regime, you indeed start off like the ideal gas. And here the motto, so the important motto of statistical physics is really this one. Given that you give yourself some rules for the interaction between two particles or several particles together, how can you recover macroscopic property like, say, an average pressure when you fix the density and the temperature? And so that will be, it will really be my goal today to explain you how to compute one of those crosses on this diagram. Another motivation, so that's closer to the numerical microscope, is biology, for instance, in which you have complicated molecules like this one. It's called ubiquitin because it's present in every cell in our body. And you would like to know how this molecule changes shape as a function of time. So when you look at a movie of that, atoms are giggling in a somewhat erratic manner, but you don't see any global motion until some point where you've got some global change of the protein. So we'd like typically to know what are more or less the typical average shapes of the molecule in time and how the molecule changes shape. So it's something which I will not be talking too much about today, so it's really this transitioning from one state which is more or less stable to another state which is more or less stable. But, well, since it's a general introduction, you should keep in mind that this is one of the major aims of molecular simulation as well. So really this numerical microscope, computing reactive trajectories and so on. So let's start setting the stage. So the first thing to do is to tell you what are the unknowns in my problem. So the unknown in my problem will be the microstate of the system. So the microstate will really be the set of all positions of my atom, which are of particles, they are capital N particles, and all their momenta. So momenta is a mass times velocity. It's not something which is very intuitive as such. Velocities are more intuitive, I think. But it turns out that this is the correct formalism because the Hamiltonian dynamics is naturally posed in terms of positions and momenta, and not position and velocities. So you have got a very large vector which describes really the microstate of the system. So when you know that, you know everything about your system. Of course, in actual systems, you never know the complete microscopic configuration because you don't know the position of every atom with an arbitrary position, and you don't know the velocity of all the atoms as well. So it's really, I mean, the microstate, it's convenient to have in mind that this gives the full information of the system, but this will not be the way we will think about it in the next slides. So in the simplest case, your positions are, well, the momenta can assume any value, and you can have positions which are either in the full space, like if you think about one molecule in vacuo, or you can have positions in periodic spaces. And so maybe it's a good time to go here. When I say that my positions are periodic, it's in fact because I think of something like that, so a fluid. A fluid is something which is very large, and I want to study the fluid in a bulk state. So if I take some simulation cell and I put, say, hard walls or whatever, since my simulation cell will not be so large, because I have 10 to the 6 particles, so it's some simulation cell of the length is about a few nanometers, maybe a fraction of micrometer. Still, it's something which is very small, and so surface effect will dominate. So the aim in molecular simulation, we have to simulate something which is in bulk state, and so one way to avoid surface effects will be to use periodic boundary conditions. So in this case, a particle which is here is periodically replicated everywhere, and here you've got somehow in front of this particle you also have a fluid in the more or less the same state, and so this allows you to have this internal region is more or less in a bulk state. So that's why people like periodic boundary conditions in molecular simulation, and I will more or less always assume in this talk today that I will be working with periodic boundary conditions, which is relevant for condensed matter simulations. Of course, there are more complicated cases when there are molecular constraints. So say if two atoms, instead of resolving a bond vibration like that, you say that, okay, let's assume that the bond is very rigid and that my two atoms are really, are fixed to are linked to a fixed bond, then you have some molecular constraint because the distance has to remain always constant. And so in this case, not all velocities are allowed because you don't want this distance to change. So then this puts some constraints, and you in fact working on a submanifold of this full space. Okay, so that's microstate, that's the set of all unknowns, and a very important function is the Hamiltonian, which gives the energy of a microstate. So the energy, in the simplest cases as well, is the sum of two terms, a potential energy and a kinetic energy. Kinetic energy is very simple, it's the sum of 1/2 mass times velocity square. That's just a fancy way of writing that, so it's the standard kinetic energy. And then to that, you add a potential energy where all the physics lies in. So it's really the aim of people in condensed matter physics or chemistry will be to provide very nice, very accurate, very fine potential energy functions. As a mathematician, I assume that this potential energy function is given to me by God or the chemist, depending on the situation, and I work with it. So one example, just to give you one paradigmatic example of potential energy function, would be for the Lennard-Jones fluid. So in this case, the total potential energy of capital N particle will be the sum of pairwise interactions, and pairwise interactions which depend only on relative distances. So the typical potential energy function for two particles, depending on the relative distances, will be this little v function, which has this shape. So at long range, you've got some van der Waals interaction, which scales like -1 over r to the 6. So this really results from dipole-dipole interactions. And then you put something which has a power larger than 6, say 2 times 6, so 12, in order to have some hardcore repulsion at short distances. So in this case, when two particles, when they're far away, they weakly attract each other. There is some equilibrium distance, which is around here. And then when two particles come too close, they want to repel each other. That's because the electronic clouds would be overlapping, and this is really energetically unfavorable. So a simple model a simple potential to model this van der Waals interaction here and hardcore repulsion there would be this Lennard-Jones potential. And then you've got two parameters. You fit them appropriately in order to have the correct equation of state, so pressure as a function of density. And so physicists have proposed this model to describe argon, and this is the potential I used to compute those points here. So in this case, it's a very quantitative, it's a quantitatively correct potential. In general, life is more complicated than that, and so you would have to rely, say, on quantum mechanical computations to have very accurate potentials, and possibly, benchmark an empirical potential using some quantum mechanical computation. That would be the typical way to do. So now let's assume that my potential energy function is given and that it's a good function, although I have to say that really most of the error in molecular simulation is modeling error, and it's hidden in this potential energy function. But as mathematicians, we cannot fight with the modeling error, so we fight with the other types of error. Boundary conditions I've always mentioned. And now we come to a very, I would say the central concept of statistical physics is that you should not think of your system as being described by the microstate, so all the set of positions and momenta, That's way too much information, and this information is really not necessarily, it's too much information and it's redundant. In fact, what you're interested in are averages of certain functions of the microstate of the system. So those functions are called observables, for instance, the pressure. And what you want to compute is really averages of function of the microstate with respect to some probability measure which describes, in average, the state of the system. So this probability measure is called a thermodynamic ensemble. And how do you choose it? Well, the general rule would be that you choose the ensemble as being the least biased measure, which satisfies some given macroscopic constraints. So that's you put the least information you can in your modeling of the system through this probability measure. So the way to fix a probability measure, you have to decide whether the volume of your simulation box is fixed exactly or in average, whether the energy also in your simulation box is fixed in average, and the same for the number of particles. And then you decide, so that there is a modeling choice here as well. You decide what you want to fix exactly or in average. That determines your thermodynamic ensembles, and then you run your computations. Hopefully there is some result of the equivalence of the results of those averages with respect to different thermodynamic ensembles as the number of particles goes to infinity. So I would say that's the general rule of thumb, that you've got a probability measure and there is a function, an observable, which you want to average with respect to this probability measure. And you see that here already there will be a problem because the probability measure is a very high dimensional one, and so computing averages with respect to this measure will be difficult. So to give some flesh to this general theorem, let's turn to one specific example, the driving example today, and admittedly, I would say the most common thermodynamic ensemble used in practice, which is the canonical measure, also termed NVT, because you fix the number of particles and the volume of the simulation box, and you fix the energy only in average. And people say that you fix the temperature in this case. So a very orthodoxic way of deriving the canonical measure is to say that I want to have the least biased measure, probability measure, which is such that the energy is fixed in average. So one way of quantifying how biased, how uniform a probability measure is to resort to this quantification through some entropy, so which would be minus rho log rho d lambda. Here lambda would be a reference measure, typically the Lebesgue measure dq dp, and rho will be the density of my probability measure with respect to the Lebesgue measure. And so the conditions you want on a probability measure are that the density is positive, the density integrates to 1, and so then and in addition you assume that certain quantities ai have a fixed average. So for the canonical measure, I will want that the average of the Hamiltonian is fixed to some given energy level. So if you want, so when you maximize this entropy without constraint, you can check that the solution is formally the uniform measure. So now if you average under those constraints, you end up with those Euler-Lagrange equations. So here if you think about having only one constraint, the energy here this Lagrange multiplier alpha is related to the normalization constraint. So if you think about only having one more constraint than the normalization, which would be the energy, you replace here E is, you only count E equals 0, and you replace, well, I call beta the Lagrange multiplier here, and here I replace A naught by H. And then you see immediately that the canonical measure has this density exponential minus the energy, minus beta the energy. So this really is the Boltzmann measure. And you see that here beta, which I've write as 1 over kBt just for notational convenience, is the Lagrange multiplier of the energy constraint. And so one magic thing in statistical physics, I would say, is that this Lagrange multiplier is 1 over kBt, where T indeed is well, some kind of a physical temperature. So it's not clear that this T here should be something like the order of 300 Kelvin in this room, but it turns out to be like that. So there is really well, there is more than a formal analogy with the macroscopic thermodynamics. It's really that when you take the correct potential energy functions, you end up with some parameter T here, which can be interpreted as some macroscopic thermodynamic temperature. So if I've lost you, well, you can just wake up and say that we will want to compute averages of some function of the microstate of the system with respect to a probability measure, which will be the Boltzmann measure, where I will say that states with lower energies are more favorable and are exponentially more favorable than others. And as I increase the temperature, I'll allow more and more for higher state energies, for states of higher energies. Right. So now some example of observables. For the pressure, for instance, well, so, I mean, again here, those kind of observables, it's unclear when you first see them why they should have those expressions. And so you can think of those observables being given to you by God or the chemist as usual. So the first example would be the pressure. So for the pressure observable, you've got this expression. So there is a first part which is somewhat kinetic pressure. So when you've got particles which are very fast, if you think of having some walls in your system, they would hit the wall very strongly, and so this exerts some ideal gas pressure. So that would be taken into account by the first term. And there is a second term, which are forces times positions, and so that's a potential part of the pressure. You can think of a system, if you compress it, then atoms will want to repel each other, and so that creates some tension or some pressure inside the material. So the pressure really is the sum of those kind of two terms, and well, statistical physics is here to tell you that the correct prefactor is 1/3 times the volume in 3D, and that here there is no factor 1/2 and so on. But at least intuitively you can understand both two terms. And so if you average this function with respect to this probability measure, then you can compute the little crosses I've shown you. Another observable would be the kinetic temperature, so it's really some variance of the energy distribution. And from that you can, well, there are many more observables. One interesting one, just to show you that it can be more complicated than a plain average, is this heat capacity, which in fact is related to a variance of the energy. Anyway, the take-home message of that first half an hour is to tell you that statistical physics is about computing averages of some observables with respect to a very high dimensional probability measure, typically of a Boltzmann-Gibbs form. And so for mathematicians, this is a challenge because, as you know, computing an integral in dimension more than 2 or 3 is already a challenge, not to mention an integral in dimension 10 to the 6. So usually, when you have got such large dimensional integrals, you use some ergodic averages, meaning that you consider some appropriate dynamics which will visit the full space, and the average over one trajectory will converge to the true average. And ergodic is nice because dynamics, when you integrate the dynamics in time, the integration is in dimension 1, and discretizing something in dimension 1 is okay. So my aim will be in the next hour will be to tell you how to compute those ergodic averages using stochastic differential equations. Right, so that's sampling the canonical ensemble. Any questions until now? No? Alors, again, so here a brief recap of the problem, really computing those kind of averages with respect to this probability measure. In fact, when you look at the Hamiltonian, there is a potential energy part and there is a kinetic energy part, which is a sum of p squared, more or less. So exponential minus a sum of p squared, it's a product of Gaussians. So sampling the momenta is really something which is trivial. Momenta are distributed according to Gaussian distributions. So I mean, any good random number generator will do the job. The real challenge is computing relevant compositions, I would say, configurations where the positions are really distributed according to this measure exponential minus beta v of q, which is a very complicated measure because, I mean, all particles are intricate, there are interactions of all sorts in all directions. It's really a nightmare to find a relevant, well, a typical conformation for this probability measure. So, I mean, you should forget about sampling so independent and identically distributed position distributed according to this measure, because it's just too high dimensional, you have no control on that. I'm just mentioning it in this slide, and then let's forget about it. Historically, there have been some deterministic methods à la Nosé-Hoover developed to sample this measure, but their ergodicity is not guaranteed. I mean, that's the bad point with deterministic methods. It's usually that ergodicity is an assumption and not really something which can be proved. So today, since I want to talk about mathematics in the end, I will present stochastic methods, so probabilistic methods, for which you can really guarantee that convergence happens. Although I can guarantee that convergence happens sometimes in 10 to the 9 years, maybe not in one day on my computer, but I mean, that's another issue. And here I make a very clear-cut distinction, like there are separations, there are people on the left and people on the right. In practice, I mean, you just mix a little bit of everything to make it work better. And so the distinction is not that clear-cut when you talk to really people implementing the algorithms. So my paradigmatic example today will be this Langevin dynamics. So I've write it here as a motivation, and really my aim would be to allow you to understand a little bit the properties of this Langevin dynamics and how it can be used in practice to compute average properties. So the Langevin dynamics can be seen as a stochastic perturbation of the Hamiltonian dynamics. So the black part is Hamiltonian dynamics, which means that derivative of position is velocities. Derivative of velocities is a sum of the conservative forces. And so that's mass times acceleration equals sum of forces. So that's something which is very well accepted, I would say, in the physics community and even the mathematical one. And so the Langevin dynamic, so the Hamiltonian dynamics is nice, but it preserves the energy. So the energy h of q and p is constant. So if you want to sample exponential minus beta h, you want the energy levels to vary. And so you cannot use Hamiltonian dynamics. There is no way that Hamiltonian dynamics is ergodic for the canonical measure exponential minus beta h. So this is the reason why you add two terms to the Hamiltonian dynamics. One friction term, which is proportional to the velocity. So that's really physically a friction. And this is a dissipative force which will allow the energy to decrease. And you compensate by adding some random fluctuation term which will allow energy to grow up again. And so there is a balance between the friction and the fluctuation which is encoded in this fluctuating term, in this term here in front of the fluctuating Brownian motion. So the square root of 2 gamma over beta. It's not clear at all why it should be square root of 2 gamma over beta and not, say, gamma squared over beta or whatever. My aim today, one of the aims today will be to motivate why this really should be square root of 2 gamma over beta here. So when you do that, I claim, and I will show you some elements of that this dynamics is ergodic for the canonical measure. And so if you integrate in time and compute the average of A and QT PT dt over time, then you really converge to canonical averages. Okay, and so so it's a nice dynamics as such, and it can be extended in various ways to sample all other types of ensembles. So it really should be thought of something paradigmatic. So my aim in the next hour will be to allow you to understand better the meaning of this equation, in particular this term dWt, which is a Brownian motion, at least in an intuitive way. Understand why it really is ergodic, how you implement it on a computer, and what are the errors you do when you implement that on a computer. And then in the last half an hour, we'll see how to use those kind of dynamics to compute transport properties like mobility, self-diffusions, and so on. Right, so first I will do a general introduction to stochastic differential equations from a pragmatic viewpoint, I insist. I will not talk about filtrations, and then we will apply it to Langevin dynamics. So the first thing is to, for those of you who have, I guess that maybe everyone has heard about Brownian motion, but it's good to recap it and to recap it in the way I need it for a numerical simulation. So the way I will be needing it in numerical simulation is when you have an SDE, which is this one, so dQt equals sigma dwt, you should think of that as the limit as delta t goes to 0 of this numerical scheme, where the new position is the previous one plus some random increment of order square root of delta t. And I mean, SDs in practice, here is really the fundamental thing is that the random terms are scaled by square root of delta t and not delta t as for deterministic drifts. And here GNs are simply independent Gaussians, which are independent and identically distributed Gaussian random increments. So you have a new position, you sample a Gaussian, you move a little bit in this direction, then another one, and this is a very erratic motion, but if you look at it over a very long time, you've got more or less some kind of diffusive behavior. So the way you can make that precise is to know that when you have a dynamics like that, it's a simple computation to show that since this is a sum of random, independent Gaussian increments, Qn is distributed according to a Gaussian distribution centered on the initial position and with a variance which is sigma n dt. So when n times delta t is fixed to some physical time t, you see that you've got a Gaussian which is a variance t, which means that indeed you've got a diffusive behavior because the standard deviation is the order of square root of t over time intervals t. Right. So how to make that a little bit more mathematically formal and go to the Fokker-Planck equation is the content of the next slide. So for that, I introduce a very central element, which is the law of the process. So here, when I've got a stochastic differential equation like that, I can think of that as starting from some initial conditions, which may be deterministic or random, and then looking at all possible Brownian motions starting from this initial position. So what I can do here is start from Q0 equals 0, for instance, do one trajectory with a certain set of Gaussian random numbers, another trajectory, another one, infinitely many ones, and I look what is the distribution of the ending points. So this is encoded in this in the law psi t of q of the process qt at time t, and it really, I mean, from a pragmatic viewpoint, it can be thought of as the histogram of all possible realizations at a given time. And so in this very simple example of Brownian motion, we would like to make contact between this distribution of positions and some heat equation. And so the way you do that is through this formula here. Is that the average of some property at time t can be seen as the average of this observable A of q against the probability distribution of positions at time t. And this probability diffusion at time t evolves according to the Fokker-Planck equation. So I will prove that in the next slide. So from that you see that indeed you've got some diffusive behavior, and if you consider the histogram of ending positions, it's something which diffuses in time. And that's why people talk about those SDs as being diffusion equations because of this diffusive behavior. So the important thing here is to motivate why this probability distribution would be evolving according to this equation. The reason being that afterwards we will be looking for steady-state solutions of the Fokker-Planck equation in order to characterize invariant measures. So the proof is here. I won't go into detail into the proof because you have the slides. Basically, it's Taylor expansion up to second order because you've got a square root of delta t. And so if you want to keep track of terms of order delta t, you have to go to second order. So you write your Taylor expansion here. So remainders are fractional, right? That's one thing. And so the not very nice thing is that here you've got the leading order term is a square root of delta t because of the Brownian part. And that's why you take an expectation and this term disappears, and so you end up with that. So that's the kind of miracles which happens when you take expectation, like in Antoine's talk yesterday. That's why it's nice to take expectations. So you have that. Now you rewrite this as this equality as this one. So you see that the average of or the expectation of this quantity goes to 0 as delta t goes to 0. So here this term, well, it's you can really rewrite it like that as the average of Laplacian of A. And this term, as delta t goes to 0, you will believe me, I guess, that this converges under reasonable assumptions to the time derivative of the expectation of time t, which is this quantity, because we've seen in the previous slide that the expectation at time t is the average of AQ with respect to the probability distribution. And so then the conclusion is that the integral of A with, against the time derivative of the probability distribution is equal to sigma squared over 2 the Laplacian of A. And then when you do some integration by parts, you obtain this equality, which tells you that indeed psi has a diffusive behavior and satisfies some heat equation. So in the end, obtaining those kind of Fokker-Planck equation is really not some magic. It's really a Taylor expansion and taking averages. Now this can be, now once you've understood that, with a little bit more algebra, you can do it in general for general SDs of this form. So first, a drift part, a bxt times dt, which is some drift part, and then some diffusive part, where in front of the Brownian motion, I may, here I may consider what is called a multiplicative noise, which means that the diffusion coefficient here may depend on the state of the system. If you're uncomfortable with this writing, I mean, you can really think of it as being the limit as delta t goes to 0 of this numerical scheme. So again, in front of the drift part, there is a delta t as usual, but in front of the random part, there is a square root of delta t. And here Gn are random Gaussian increments. And when you see an SD like that, you can associate to that what is called the generator. And so the generator is you consider the drift part, and then the operator corresponding to that is a Bx scalar gradient. And then associated with the diffusion part, you've got 1/2 sigma sigma transpose concatenated with the Hessian. And a more well, if you want to write this in terms of coordinate, it would be this matrix times this double derivative here. So you see that the generator is some elliptic operator, which may have some degenerate ellipticity, but at least it's some elliptic operator, which again motivates the terminology diffusion equation for those kind of SDs. And proceeding as I did before, so you would be doing, you would be starting from this numerical scheme and looking at what is A of xn plus 1 in terms of A of xn and its derivative. You can work out that the derivative of some average property at time t is given by the average of the generator applied to A times the probability distribution psi. So that's the interest of the generator. It tells you how average properties evolve in time. So for those of you who know quantum mechanics, this would be somewhat the Heisenberg picture of looking at evolution of observables. And so once you have that, you see that from that you can derive the Fokker-Planck equation as being dt of psi is the adjoint of L applied to psi. So that's the way it works. So it's written over there. So that's really the Fokker-Planck equation. So the conclusion of that is that if you are given a SD like that, you write down the generator by just reading off those two coefficients, taking this general form, you've got your generator, you compute the adjoint on the flat L2 space, and then the evolution of the probability distribution would be this one. And that's the Fokker-Planck equation. And so this is an equation which is, I mean, there is less information in the Fokker-Planck equation than in the SDE because you don't have information on the individual paths or realizations, but this at least describes the average behavior of a large collection of systems, I would say. So and in particular, it's sufficient to compute average properties as we want. So stationary measures now for a stochastic differential equations are a stationary solution of this Fokker-Planck equation. If you start from a stationary measure psi infinity, so if initial conditions are distributed according to psi infinity, you evolve your SDE, you consider all passes starting from all possible initial conditions. You don't see anything moving. So if you look at the histogram remains constant. Even though each point may move, when you see that from very far away, it does not move. So probability measures are eigenvector associated to eigenvalue 0 of the Fokker-Planck operator, and they should be normalized to 1 and positive. So the question is whether such solutions exist, and so in the case when the operator is elliptic, so when the noise is sufficiently rich and the sigma transpose has full rank, then you can show that this is indeed the case. And the way it works is that first you show that the process is what is called irreducible. So you can, starting from any point, you can reach any set of positive measure in finite time. So you can go from anywhere to anywhere. That's irreducibility. Just to ensure that the dynamics will visit the full space. Now to say that the dynamics will visit the full space with the correct weights is something which is a general result which shows that if you have, if you know that there is some invariant probability measure, which need not be unique at this stage, and you know that the process can visit the full space, you automatically know that that the invariant probability measure is unique. And so it's the one you think it is. And more or less, in this case, you've got these ergodicity properties that averages over one trajectory indeed converge to averages with respect to the invariant measure. So the rule of the game here is first to identify an invariant probability measure, and then to make sure that your process is sufficient, well, that the noise in your SD is sufficiently rich so that you can go from any configuration to any other one. And once you've got those two requirements, then you're in business, you know that your method is ergodic and that you almost surely converge, well, that averages over one trajectory almost surely converge to averages with respect to the invariant measure. So that's the first good news, I would say. The second good news is that, well, you'd like to know at which rate you converge. So you cannot really expect much more than a central limit theorem. But even obtaining a central limit theorem is not something which is completely clear, because here you've got some stochastic process where there are some correlations in time. So you need some central limit theorem which allows to take into account those correlations in time. And that's something which indeed is granted in this, well, for dynamics which are sufficiently nice. So the precise statement is that when you look at the average over a time frame capital T, capital T is not a temperature, by the way. I should have mentioned that earlier. I will only write beta for temperature. That's the reason why I never talk about temperature, in fact. So when you consider average over a time frame capital T, you subtract the average with respect to the invariant measure, and you rescale that by square root of delta T. This converges in law to some Gaussian distribution with some variance. So, and this really tells you that averages over one trajectory is what you want, plus some error of order 1 over square root of T. And this allows you to have confidence intervals and so on. Of course, what you like to know in practice is what the variance is, so that would really help you estimate the errors you're making. Unfortunately, because life is not as beautiful as it should be in all situations, the variance has a complicated expression, and it's not and does not have an analytic expression. So you will have, I will have to show you how to estimate it in practice. The analytical expression, on the other hand, is given by this integrated correlation function. So it's a simple computation. If you take this average, you square it, you take the expectation, and that should give you the variance. And when you do the computation using the stationarity in time of the process, you see that you end up with this expression, then you pass to the limit. As time goes to infinity, you obtain that. So it's not clear at this stage that this is a well-defined quantity, and it's not clear whether it's large or not. So that's the reason for but at least under good circumstances, there is a central limit theorem, and for practitioners, I mean, that's already an information. For mathematicians, you'd like to know whether the variance is well-defined. So the first thing is to rewrite this variance here in terms of operators. I mean, that's because I may be talking about stochastic differential equations and so on. I fundamentally am someone from analysis, and I like to see operators rather than expectations. So I first rewrite my variance like that. So exponential TL of phi tilde gives you, well, maybe. You have to believe me that this expectation here can be written like that. So you consider initial conditions which are distributed according to the invariant measure. There is a phi tilde x here, and exponential TL of phi tilde x. Maybe I should write it on the board, provided there are some chokes. On the desk, merci. Exponential TL of phi of x. This is the expectation of phi of xt, given that x naught starts at x. I should have written that in the slides. So if you use this semi-group rewriting of the expectation over realizations of the dynamics, you see that you can rewrite the variance in terms of this operator equality. And now, using formally the fact that the integral of exponential TL is L minus 1, you can rewrite the variance like that. So in order to really rewrite this in this way, you need some exponential decay of the semi-group in some appropriate functional space. And so that's where mathematics starts. So you really want, sorry, here it should be an exponential TL. So it's really exponential TL, which I want to bound by something which is exponentially decreasing. And so here mathematics starts. There are different functional settings to make it work. The most general setting, when you don't know, when you don't have a structure on your SDE, would be to be using Lyapunov conditions and so work in weighted and infinity spaces. Well, that's one thing. If you want to know more about that, there are two papers written in for people liking spectral theory and more analytical arguments than probabilistic arguments. And so I really recommend them to you if you want to enter the domain. It's much easier to read than the probabilistic paper. So that's, I mean, in general, you've got those kind of Lyapunov conditions, which I won't be talking much more about. But for specific dynamics, like the ones we will be considering today, you may have other functional frameworks which are much more suited to the structure of the equations. So for what is called overdamped Langevin dynamics, there will be logarithmic Sobolev inequalities, Poincaré inequalities. And for Langevin dynamics, there is hypocoercivity and subelliptic estimates. And I will come back to that. So remember at this stage that for mathematicians, there is a job in making sure that the semi-group is exponentially decaying. If the generator is elliptic, it's usually granted. But if the generator is not elliptic, the situation is more complicated. Okay, so that's the end of generalities on SD at the continuous level, and the main aim was to say that, well, you've got some ergodicity result, and you've got error estimates using a central limit theorem. Now, in practice, of course, we have to discretize the time, and so I have to tell you a little bit about numerical schemes to integrate SDs. So SDE, when you discretize it, it becomes a Markov chain, because time is discrete, and the new state depends only on the previous state and not the history before that. So a typical way to discretize the SDE, which is here, is to use this Euler-Maruyama numerical scheme. It's often not the best thing to do in practice because the errors may be large, but I mean, at least for first presentation, that's the best thing to do. And so there are several notions of errors for SDEs, and there are more notions of error than for ODEs, where you essentially look at the error on trajectories over finite time intervals. So there are several ways of measuring the error. The two most common ways are to measure errors on finite integration times by either looking at what is called a strong error, so really errors between realizations of the paths, or rather looking at weak error, so only looking at differences between averages over the configurations. So here you can see it's rather like an average of the error, and here it's rather like an error on the averages. So this second notion, the weak error, is something which is less demanding than the first one, the strong error. In molecular simulation, we are more interested in average properties, so averages over many configurations, so it's rather weak error type results we want, except that we want to have them at infinite times because we are looking for averages over infinitely long trajectories. So in essence, it will be none of those two errors which will be relevant. But it's good to have those standard notions in mind. Alors, so for numerical simulation, as I've just told, I will not be using weak error nor strong errors, but rather errors over trajectorial averages. So once I've discretized my dynamics, I consider some observable phi, and I compute its average over the discrete numerical trajectory. So the first thing is to say that, well, I have to prove that my numerical scheme is indeed ergodic for some invariant measure, which will be a priori a little bit different from the invariant measure of the continuous equation. So there will be some perturbation in the invariant measure because I've discretized time. So first, you need to show that. Once you have that, well, you can say that typically the average over a trajectory at a finite horizon is the sum of two things. First, it's the average with respect to the invariant measure plus some error which is related of the finiteness of the number of iterations. So this second error, the finiteness of the number of iterations, is typically given by a central limit theorem as for the continuous case. And you see here there is a variance which may depend on delta t, well, which depends on delta t, in fact. And this second term is scaling as 1 over square root of the number of iterations, which is a good and a bad news. A good news because it does not depend on the dimension of the system. It can be 10 to the 8. You don't see it in this scaling here, but you see it in the prefactor, of course. On the other hand, so that's the good news part. The bad news part is that this is something which is decaying very slow, and if you want 1% precision, when you know that your current computation, which took 1 week, has 10% errors, we know that you have 10 weeks to go. So that's a statistical error, which is quantified in the usual way. And there is another error, which is here, which is a systematic error related to the fact that the invariant measure for the numerical scheme is slightly different from the invariant measure for the continuous dynamics. And so that's what I call a perfect sampling bias. And so I'll show you some elements on those two errors today. Est-ce que c'est un... Well, maybe it's a good time to stop for a few minutes just to stretch your legs and get refocused. Ouais, 5 minutes, yeah. So welcome back. Alors, I mean, talking will, of course, make everyone scream into the room. So we were at numeric. So the point is that we discretize our SDE using a numerical scheme. We want to compute averages over a discrete trajectory. There are two types of errors, statistical one and a systematic bias. So next slide is about estimating this statistical error, because of course, as I tell my students, a computer will always give you a number. The point is, how much do you trust your number? And if you ask Andra, I mean, they want to know how much you trust your number so that they can trust it. So you need to estimate errors. I mean, estimating the error is almost as important as obtaining the number in itself. So this means estimating this variance. This seems again like a daunting task because there are averages everywhere and it seems quite complicated. So first thing is obtaining the expression of the variance, and you see that in very strong analogy to the continuous case, it's the sum of two things, the variance of points considered as being independent, which is a small contribution, and then some autocorrelation term. So a sum of the integral of the expectation of a value at xn times a value at x naught. In fact, a simple computation shows you that this variance is more or less 2 divided by delta t, the expectation of the continuous dynamics. So it really tells you that the prefactor here is 1 over delta t, and this in fact is not unmoral, because when you look at this variance, this means that here the prefactor is more or less 1 over the number of iteration steps times delta t, so 1 over a square root of the physical time. So that's really what you expect. And so this also shows you that it's really this part of the variance which is important. The proof of this equality, I mean, it's the same as before. You take the square of the average, you multiply by the number of iteration steps, you use some stationarity, and then you obtain the formula quite, well, you obtain the formula very fast. Now, I mean, to estimate that in practice, I won't go into the details, but there is something which is called block averaging, where you take a very long trajectory, you cut it into sufficiently large blocks, you assume that you have a central limit theorem in each block, and from that you construct an estimator of the variance for the full trajectory. And so one last point before turning to the applications is that, so it's nice to know that you have got a central limit theorem, but in practice, you observe that the variance is very large. And the reason why the variance is very large is something which is called metastability. Is that for typical molecular simulation applications, you have long-lived states, which are called metastables. So the system remains trapped in some states before hopping to another one where it also remains trapped for a very long time, and so on and so forth. So two paradigmatic academic examples are this one. So this is a double well potential in 2D. So you've got one minimum here for the potential energy function, one minimum there, and so there are two pathways to go from one side to the other. So either here, either there, and so this is a hill. And so when you look at a typical trajectory for a typical dynamics, which I will present afterwards, you see that you remain stuck. I mean, you giggle around here, and then at some point you go to the other side, and you remain trapped, and then you go to the other side, and so on. And so the time series of the x coordinate as a function of time is something where you remain a very long time at -1, then you switch to 1, and then you switch back to -1, and so on. And so if you are to compute the average position as a function of time, this is something which will converge to 0, I can guarantee you that, but it will do at a very slow rate. So the prefactor in front of the 1 over square root of time for the statistical error will be very large, and much larger as you decrease the temperature. Another example is this entropic barrier potential. So here the potential is plus infinity outside this bone-shaped region where it is 0. So the dynamic can freely move here. So it will freely move here until it finds its way to the other side, and then it will freely move there. So here in this case, there is no energetic barrier which prevents going from one state to the other one. It's an entropic barrier. It's simply that the path is too narrow, and if you explore it in a diffusive manner, it will take you a long time to go from here to there. The analogy being, if you are in a large room in the dark, there is one door somewhere and you want to find it, it will take you quite some time to find it, even though it doesn't cost you anything to walk around. Whereas the first example would be rather that you're in a valley, you want to go to another valley, and you cross the mountain to go on the other side. So this will take you time because you have to go uphill. And so this is really a pain in practice, it's this metastability, because it is the source of large variances, and so you need in practice variance reduction techniques to compute averages much more efficiently. So I won't be talking about that today, but really bear in mind that this is a very important topic to make things work in practice. So now, to the dynamics relevant for Andra-like applications and applications in statistical physics in general. So the first dynamics I want to consider is the overdamped Langevin dynamics. I start with this one because it's a limit of the Langevin dynamics, but a nice limit because the generator you obtain is elliptic. So the time evolution of position is driven by two terms, a minus gradient d energy. So this term allows you to decrease the energy of the system, and then there is a random fluctuating term which allows the energy to go up. And so here again there is a precise balance between the two terms, which is encoded by the square root over 2 beta prefactor in front of the diffusion. And here this prefactor is chosen so that the exponential minus beta v is an invariant measure for this dynamics. So the way you see that is that you write down the generator of this dynamics. So it's minus grad v nabla q plus 1/2 1 over beta de Laplacian. So using the general rules for SDs I've presented before. You compute the adjoint of this generator with respect to the L2 scalar product, and then you obtain this operator. And then you simply replace phi by exponential minus beta v, and you realize that this quantity, well, what is into those brackets, is 0 when phi is replaced by exponential minus beta v. So the canonical measure is an invariant measure for this process. On the other hand, here the noise acts in all directions, so proving that the dynamics is irreducible is not really complicated. And so you can really immediately say that this dynamics is ergodic. And the way to think about it, if you do not really like the continuous form with the Brownian motion, is really as the delta t goes to 0 limit of this numerical scheme. Right, maybe I'll skip that. So I mean, this is one way to do. When you do that, when you do this numerical discretization, you've got an error on the numerical on the numerically invariant measure, because I mean you've discretized the time, and one way to remove the bias and so to correct for the errors in the invariant measure would be to superimpose a metropolis rule to this discretization. So this is what this slide was about, but probably I'll just skip it. And I'll just advertise the fact that if you want to remove bias, so systematic errors related to the incorrectness of the invariant measure, you can use a metropolis procedure, which in a nutshell is simply accepting the new positions Qn+1 according to some probabilistic rule. And by doing that, you can correct for biases. By doing that, you automatically ensure that exponential minus beta v is the unique invariant measure for your Markov chain. So let's skip that. So this was overdamp Langevin dynamics. And now I go to Langevin dynamics. So this was really the paradigmatic dynamics I wanted to present you. So I recall you that Langevin dynamics is this one. Here, gamma and sigma, you can think about that as positive scalar numbers, but there might be matrices as well, and those matrices may depend on the position. I mean, it's only a minor technical complication. The generator for this dynamics is the sum of two terms. First, there is a Hamiltonian part, which is here. So it's a transport. It's a transport part. So a first-order differential operator, where you've got which is given by this expression. And then there is a fluctuation dissipation term, which I call a thermalization part, which is given by this expression. And maybe, I mean, think about a scalar sigma, and then in this case, this second term is simply a sigma squared divided by 2 Laplacian in P. So first thing is that you can show that this dynamics is irreducible. It's not something which is completely clear, because the noise acts only on the momenta, and whereas irreducibility asks you to control both positions and momenta. So you have to make sure that starting from somewhere with a certain velocity, you can end up anywhere else with another velocity. And so it can be proved, in fact, that the noise is sufficiently rich so that it transmits from the momenta to the positions. So you can really drive the momenta in order to end up to the correct positions with the correct momentum. So it's a simple control argument. In fact, it's not that difficult, I would say. That's the first thing. The other thing is to make sure that exponential minus beta h is an invariant measure for this stochastic differential equation. And so this asks for finding the correct sigma for which this is the case. So the way you do that is you write down the generator of the dynamics, which we've done in the previous slide, and compute its adjoint. In fact, here there is a nice structure in this equation which tells you that the Hamiltonian operator, in fact, is anti-self-adjoint, is anti-symmetric at least. This is because if you take the adjoints here, I mean there is no p dependence here, so you simply transform the signs of those first-order differential operators. So this, since you have that, and since a simple computation shows you that energy is preserved by the Hamiltonian part, you immediately have that the Hamiltonian operator applied to any function of h is equal to 0. So in particular, L Hamiltonian applied to exponential minus beta h is equal to 0. So we only have to understand what happens to the fluctuation dissipation part. So when you look at the fluctuation dissipation part, you see that it's something which depends only on P. And now, with the eyes of love, you recognize that here it's more or less an overdamped Langevin dynamics where with a potential with a force m-1p instead of gradient v of q. If you look at this blue part, and I go a few slides before, you really see that it has the same structure, except that here there is a minus gamma m-1p. So this calls for a potential which is p squared divided by 2. And so by doing the same manipulations as for the overdamped Langevin dynamics, you can see that exponential minus beta p squared divided by 2, or this more complicated notation, is equal to 0. So here you see that any function of h is invariant for the Hamiltonian part, and exponential, and this Gaussian is invariant for the fluctuation dissipation part. So this shows that exponential minus beta h is invariant for the two parts, for the two pieces of the dynamics. And this, and this motivates the fact that here you should have 1 over beta, and which determines sigma to satisfy this fluctuation dissipation relation in matrix form here, but otherwise with scalar it would be sigma squared is equal to 2 gamma over beta. Okay, so we have irreducibility, we have invariance of the canonical measure, so we know that the Langevin dynamics is ergodic. So it's a good dynamics to compute averages in practice. So maybe some functional estimates now. In order to have a finite variance and so on, you remember that we needed some exponential decay of the semigroup. So for overdamped Langevin dynamics, where the generator is elliptic, this is more or less standard business, especially if we are working on a compact state space, as we do when we have periodic boundary conditions. For Langevin dynamics, it's not as straightforward because we have an operator which is hypoelliptic, so an operator with a degenerate diffusion. And so obtaining the correct functional estimates is something which is much more difficult. So this slide is about advertising the fact that in the previous 10 years, there have been a work in the functional analysis and spectral theory worlds about that. So starting with some work by Denis Tallet, and then the subelliptic estimates of Jean-Pierre Ekman and Martin Herrer and Frédéric Hérault and Francis Nier. I was about to say the wrong name. And then this was taken over a few years later by Cédric Villani with his hypocoercivity theory. And so the basic, the core of the subelliptic estimates is to write the operator as the sum of some anti-symmetric part x0, which is the Hamiltonian part in this case, and then a sum of, and then minus a positive operator, which is in this x square x form. So here you see there is a dissipative part, although it acts only on P, and there is an anti-symmetric part which acts on every one. And so, provided you have some commutator structure between this part on P and this anti-symmetric part, you can conclude to decay in all variables. So the typical framework for that would be to work on L2 spaces weighted by the invariant measure exponential minus beta h. And so then using those kind of results, you can conclude that you've got some exponential decay, and that the inverse of the generator is that the generator has a compact resolvent on the orthogonal of its kernel. And so typically the spectrum of this operator L-1, the spectrum of L on this space L2 of psi naught deprived from the kernel would be of this form. So you would have some kind of a cusp region here in which the spectrum is contained. So it's not a sector operator for which the spectrum would be contained in some between two lines like that. But it's an operator for which the spectrum can, it can go quite high in the imaginary parts here. But the point is that you have here a spectral gap, and you can sometimes control the spectral gap. One way to have something quite explicit is hypocoercivity, which I recall here. I like hypocoercivity because in the end, it's only a few pages of computation. It's a simple well, the computations are quite simple, and it gives some structure in the equation. So the aim of hypocoercivity is to obtain an exponential decay of the semi-group in the H1 of psi naught norm. And it's said to be hypocoercive because here, in fact, you've got a prefactor capital C, which is not 1, but it's something which is larger than 1. Whereas if it was coercive, you would have here, you could replace C by 1. So for that, to apply hypocoercivity, you need some structure on the equation, and it's precisely that the x0 part here is anti-symmetric. The xi and x, there are some technical conditions on commutator bounds and so on. There is one important quantity, which is the commutator between the antisymmetric part and the xi, which I recall form the symmetric part of the operator. So you consider this operator ci. For the Langevin dynamics, a simple computation shows that it's the derivative in qi. So xi is in the derivative in p. Ci is in the derivative of q. And so a very important assumption for hypocoercivity is that this operator is coercive. Here in our case it will be because you will essentially have some Laplacian in p plus some Laplacian in q. So really this commutator structure allows you to recover some Laplacian in the variables which are not driven by the noise. And so with that you can conclude to this exponential decay in the H1 norm. And the way the proof works, for those of you who may not have heard so much about it, is to introduce some scalar product with mixed derivatives. I say mixed derivative because here you've got the L2 part, here you've got the gradient P part, here you've got the gradient Q part, and here in between you've got terms which mix gradient of Q and gradient of P. And those terms, although they are small because there is a 1 in front of them compared to a B here and an A here, which are very large. So those terms, although they are small, they are really important to obtain dissipation in the Q directions. And so this commutator structure was implicit in the work by Thaler, and it was really afterwards that, well, in the book by Villani, this commutator structure was really highlighted in all its general form. So there are really very nice structural properties of the Langevin equation, which make sure that even if the noise acts only in the p directions, you end up with an operator which has very nice spectral properties, although the noise is state degenerate. Right. So one word now just to make the link between Langevin and overdamped Langevin. So as the name suggests, overdamped Langevin is the limit of the Langevin dynamics as the friction goes to infinity. That's one way to look at it. The other way to look at it is to consider the limit when the mass of the particle goes to 0. And so, I mean, you can take either of two limits and then you can rewrite the Langevin. So let's consider the case when the mass of the particle goes to 0. Then you rewrite the Langevin dynamics in this way. So now I'm working with velocities, and that's why I put an epsilon in front of this term here instead of having dp. And so formally, when you let epsilon go to 0, you just erase this term. You replace Vt here by d of q, and so then you obtain the limiting Langevin dynamics, which is overdamped Langevin. Just to motivate the fact that the terminology has some meaning, but I prefer to show overdamped Langevin first because the generator is elliptic before going to Langevin. Right, now to the numerics. So again, Langevin dynamics is very nice, it converges, but in practice you need to discretize it on a computer and to run it in an actual code. So one way to discretize the Langevin dynamics, one way I like and many people like, is to separate, to split the dynamics between two parts, a Hamiltonian part, which you know very well how to integrate because I mean we've got a strong experience with that, and the way to integrate that would be to use some Verlet scheme, something which is symplectic and blah blah blah, and I won't be talking about that today. And another part, which is this simple dynamics where you recognize an Ornstein-Uhlenbeck process on the momenta. So if you've never seen that, just believe me, this can be integrated analytically. And this part here, it's very well documented how to integrate it. So it's a very natural way of splitting the dynamics into two parts, which you know how to integrate. So for this second part, you can do this little computation and show that the analytic evolution I was mentioning was this one, is that if you start from P naught at time t, you've got momentum, which is the initial momentum decayed by an exponential factor plus some random fluctuation term, which you very well know. So when you do that, when you integrate this Hamiltonian dynamics over a time step delta t using a Verlet scheme, and then this Anschal-Uhlenbeck over a time delta t using this analytical formula, you end up with this numerical scheme. I mean, I don't want you to understand all the details of it, but I mean, simply, I just want you to see that there is a first part, which is integration of the Hamiltonian dynamics using a very nice scheme called the Verlet scheme, and then this fluctuation dissipation part. And of course, there are many other ways to split the dynamics, to integrate it in various orders and so on. And it's sometimes a matter of taste, which method you prefer to implement. In practice, people like those kind of things because in molecular dynamics codes, typically Verlet is implemented. And if you want to turn a Verlet scheme into something which simulates the Langevin dynamics, you simply add some partial refreshing of the momenta. Okay, so that's the numerical scheme. Now what we would like to, at least what I want to understand, is what is the errors provided by that arise from the discretization of the scheme. So for that, I introduce what is called the evolution operator. So it's the numerical counterpart of this semigroup exponential TL. So it's an operator which to a function psi associates the average of psi qn plus 1 when at the previous step you were starting from Q. So you start from Q, you do all one-step evolutions of your Markov chain, and you average the result. And so this gives you P delta T of psi. So it's some kind of a discrete time evolution operator. So the invariant measure for the numerical scheme, provided it exists, but in this case it exists when the position space is compact when the position space is compact. So the invariant measure for the numerical scheme satisfies by definition this equality. If you start from initial conditions distributed according to the invariant measure for the numerical scheme, you evolve over one time step, you do not change the configurations you have. So this really is encoded in this equality. So now what we would like to understand is how this invariant measure mu underscore delta t is close to the actual Boltzmann-Gibbs measure exponential minus beta h. And so for that, there are results like this one, which go back to Talen-Tubaro in the beginning of the 90s for other types of equations, which tell you that averages with respect to the numerically invariant measure are actual averages plus perturbations of order delta t to the power something. And then the power something depends on how you've integrated your dynamics. And then there are remainder terms, which also depends on the way you've integrated your dynamics. And also what you can make precise, really what this leading order correction is in terms of a solution of some Poisson equation of the form L star of f is equal to something. So I mean, so that for those of you who want to see the proof, in fact, in this case, it's not too complicated because due to this simple structure here, I can split my evolution operator as the composition of semigroups with respect to elementary evolutions where I evolve only positions, only momenta, or I do the fluctuation dissipation. So just believe me, I can write down my evolution operator like that. Then I use a BCH, Baker-Campbell-Hausdorff formula to write down that, in fact, P underscore delta T is equal to this series, which I've truncated here. So and here this commutator is really appearing because of the BCH formula. And there is some algebraic miracle here, which makes sure that even this commutator, even though the second term is not L squared, but a perturbation of L squared, this does not change the invariant measure, and so you can really characterize the change in the invariant measure by this S2 term. Anyway, so for those of you who want to see that from a more general perspective, I would say, just bear in mind that once you have a numerical scheme, you've got an evolution operator, You can tailor expand it by using finite differences, taking averages and so on. You've got an expansion as operators, and from that expansion you can characterize how good the invariant measure is and compute the leading order correction. And for those of you who want to see the proof, I've provided it in the slides. So now to the last part, I want to close on that, on the computation of transport coefficients. So until now, we've seen how to compute average properties like a pressure, something which is static, by simply sampling the Boltzmann-Gibbs measure. So until now, although I've used dynamics, I've not used dynamical information. It's simply a way, a convenient way, and maybe an unphysical way of sampling well, making a list of typical configurations. Now, I'll discuss another topic, which is computation of transport properties, so something which really depends on the dynamics. So what you would like to compute, for instance, is a shear viscosity, a thermal conductivity, a self-diffusion coefficient. So for that, dynamic matters, and we have to understand how it matters. So from a very general perspective, there are three ways of computing a transport coefficient, and they are all analogies to what you would be doing at a macroscopic level. So first, there are equilibrium techniques, which are based on the Green-Kubo formula and on the regression of infinitesimal perturbations. You say that you've got a material at equilibrium, you do a little bit perturbation here, and you look how the perturbation decays as a function of time. And in fact, it's quite close to those transient methods for which you do a large perturbation and you look at how it relaxes. And then there is another class of method where you put some forcing on the system and you look at the average response. So for instance, for thermal transport, you heat one side of the solid, you cool the other one, and you look at what is the energy flow from the hot to the cold side. And by measuring the average energy current and dividing by the temperature difference, you recover the thermal conductivity. So those are the two, I would say, two main ways, those equilibrium correlations and those steady-state non-equilibrium techniques. And so from a mathematical viewpoint, the question we'll have to ask ourselves are whether the correlations that appear are integrable, and so that's related to a decay of semigroups. And for steady-state non-equilibrium situations is whether we indeed have some invariant probability measure. And in this case, it's not as nice as for Langevin dynamics and so on. Because of the perturbation terms, we lose some gradient structure or some hypocoercive structure. So, I mean, it requires other kind of techniques which may not be as precise as before. Alors, two examples. I mean, it's good to have an example to motivate everything. And maybe let's focus on the first one. So it's the Langevin dynamics in black, the one we've seen before. And now what I'm adding is some constant forcing in some direction f. So think about one particle in a periodic box, which we periodize over full space. So let's think about one particle in the full space in a periodic potential. So typically the particle would be diffusing like that over very long times. Now what we do, we push it in one direction. So it has an erratic behavior, but we always push it on the left. So what we will see is that the particle will have some erratic motion, but in average it will go to the left at a certain velocity. And so what we want to know in this case is depending on the magnitude of the forcing here, so on the magnitude of eta, what is the average velocity in the direction in which we push the particle. So we expect more or less that the particle will move proportionally to eta with some proportionality constant, which is called the mobility. And so that's one typical thing we want to measure. An alternative way to do would be to consider no forcing and simply let the particle diffuse in time. And so then there would be some effective diffusion. And it turns out in this case, and I will prove you that there is a precise relationship between the average velocity when you push and the spontaneous diffusion when you don't push. And both allow you to compute the mobility of the particle and so predict its evolution over very long times. So that's the first example, the one I will focus on. And just to have another example would be a 1D chain of atoms in which you put one side at a higher temperature and another side and the last side at a colder temperature, and you look at the energy gradient. just to have 2 examples in mind. And so from a physical viewpoint, in those systems, you consider them as being out of equilibrium because you've got currents. Here there is a current of energy from one side to the other. Here there is a current of particles. Maybe I should emphasize at this stage that although I'm putting a constant force here, this constant force does not derive from the gradient of a periodic potential, and that's the reason it's a non-gradient forcing term. Although it formally derives from the gradient, which would be F transpose Q, but it's not periodic. So from a mathematical viewpoint, I consider a dynamics to be non-equilibrium when the generator is not self-adjoint with respect to the invariant measure. So Overdamp-Langevin dynamics was, maybe I can go back to that. It's maybe not clear on the slides. No, it's not clear, I think. No. Here, I mean, it seems that the generator, when you look at the adjoint, it's not the same, but in fact, this dynamics is self-adjoint with respect to L2 of exponential minus beta V. For the Langevin dynamics, it's not reversible with respect to exponential minus beta H, but up to changing the sign of the momenta, it would be reversible. So simply bear in mind that Overdamp-Langevin and Langevin were dynamics which could be considered as equilibrium dynamics, whereas the dynamics here in the previous slides genuinely are non-equilibrium because the generator is not self-adjoint. And so, I mean, the first point with those kind of dynamics would be to prove that indeed there is a stationary steady state invariant measure. And we cannot, I mean, it's difficult to use the techniques I've shown you before, so writing down the generator and plugging in what you believe to be the invariant measure, because in those situations you don't know the expression of the invariant measure. So we will use some perturbative techniques to make sure that indeed there is an invariant measure. Right, so maybe let's first warn you that for non-equilibrium steady states is something which is much more complicated than equilibrium dynamics. And the reason is that there are long-range correlations and you cannot really perturb the system. Well, if you do something on the system, you can perturb it really everywhere. So for an equilibrium dynamics like this one, if I modify a little bit the bias by adding a gradient V tilde term here, I know how I change the invariant measure. I simply replace V by V minus V tilde. And in particular, if this V tilde is local in space, I only locally change the invariant measure. So that's nice. I mean, it's local perturbation and so on. If I do something here, I know how to unbias. And this is actually something which is behind many methods in reducing the variance in equilibrium systems. For non-equilibrium dynamics, the situation is really more complicated. So I consider these dynamics, so again on the torus, so this is not a gradient term. When you write down the invariant measure, it turns out that in 1D it has an analytical expression which is given by this expression. So here you see that by adding f, as small, I mean even a very small f, changes the invariant measure everywhere. From a physical viewpoint, I mean, I wouldn't say it's clear, but I mean it can be understood by the fact that this forcing term f, well, allows information to pass from one side to the other of the system, and so what you modify here has an impact on the other side of the system as well, which is not the case for equilibrium dynamics, which more or less are very local things. So with this warning, I mean, from here the conclusion is that the invariant measure for non-equilibrium system is something which is complicated, and it typically does not have very simple forms like that. And so one way to have, well, to write down something about the invariant measure is to assume that the forcing is sufficiently small and to use perturbative expansions. So that's what we are going to do now. So typically the generator of the perturbed dynamics, I can write it as an unperturbed generator plus some perturbation. Maybe I'll show you immediately an example. So for this dynamics, Langevin dynamics, the generator of the perturbation would be f scalar derivative with respect to p. Up. So the Fokker-Planck equation, now I write it on this Hilbert space here, so L2 of psi naught. It turns out, I mean, you know the reference system is the case you have no forcing, you know the invariant measure, and you want to see the non-equilibrium system as a perturbation of this equilibrium one. So it's natural to think of the invariant measure of the non-equilibrium system as being the reference equilibrium measure times some perturbation f of eta. And so when you write down the Fokker-Planck equation on L2 of psi naught, you end up with this equation here. So this would determine this f eta. So when eta is equal to 0, f eta is equal to 1. And what can be shown when this perturbation L1 is sufficiently small is that, in fact, you can write down a series expansion of this perturbation of the non-equilibrium of the equilibrium measure as this infinite series. So at leading order, it's 1. That simply expresses the fact that at leading order, the invariant measure is still very close to psi naught. And then there are terms of order eta, eta squared, and blah, blah, blah. And so they are given by these iterated powers of the operators. So to make sure that this series indeed makes sense, we have to make sure that one way to make sure that this series makes sense is to make sure that this operator here is bounded. And then it has a finite spectral radius, and then you can take eta to be as large as the inverse of the spectral radius. To make sure that this operator is bounded, we very heavily rely on the fact that we know the equilibrium dynamics, and typically we will assume that the generator of the adjoint of the generator is invertible on the orthogonal of the kernel, and that the perturbation L1 we consider is sufficiently small in the sense that those kind of equalities typically hold. So we want L1 to be L0 bounded in a sense. Well, so I mean, there are technical conditions to make sure that those kind of expansion make sense in L2 of psi naught, but in the end, seen from very far away, it's simply a perturbative expansion. And so once you have this perturbative expansion, what you will want to look at is the response of some property. So in my example of autodiffusion, what I will be looking at is, I would say, I will want to know what is the average velocity in the direction in which I'm pushing. So that will be the typical response. I expect that when eta is equal to 0, so I'm not pushing, the velocity is in average 0 because it's diffusive. And when I start pushing a little bit, the velocity will be proportional to eta. And so this is encoded in the fact that I want my response, the average of my response, with respect to the invariant measure when there is a forcing eta, divided by eta. This should have a limit as eta goes to 0. And so you can compute from this expansion of the invariant measure, you can work out what the limit should be. And in fact, you can rewrite it this way, and you can rewrite it as this integrated autocorrelation function. So this is the way to link the response of non-equilibrium systems in a linear perturbation regime with a Green-Kubo formula which expresses the transport coefficient as some integrated autocorrelation function. So that's really the basic formula. I mean, if you have to remember one thing from the last half an hour, I guess it would be that those kind of formulas exist, which is already something. And so in practice, what you have to do is to identify the response you want, to construct a physically meaningful perturbation, and then to work out those kind of limits. So to make sure, so a few references if you want to know more, but let's turn to one example and I'll finish on that. Let's consider the case of autodiffusion. So typical Andra application is self-diffusion of an ion between in some clay material, and how does it evolve over very long times. So there would be two ways to compute the self-diffusion. The first way is to consider some non-equilibrium dynamics. So I always push my particles in this direction f, and I look at the average velocity in the direction f. And when I compute the average velocity in the direction f divided by eta and let eta go to 0, I recover this quantity here. So it's the autocorrelation of the velocity in the direction f. And here I should make clear that the expectation here is with respect to initial conditions distributed according to the canonical measure and for all realizations of the Langevin dynamics, the equilibrium one. So that's called the mobility. So it's how the particle is likely to move when you apply a constant force on it. There is another important quantity, which is the effective diffusion, which now you take a particle at equilibrium, you do not push on it, and you look at how it spontaneously diffuses over very long times, and how it spontaneously diffuses in the direction f you want to consider. So you would be looking at those kind of expressions here. C'est correct, ça? I think the expectation should be outside, probably better. The expectation should be outside here. I'll correct that on the slides. In order to have this equality, I mean, you have to put the expectation outside of this bracket. Bon. Okay, so correct that in your mind, so put it outside. So once you have it outside, here you look at the typical distance square over a time t, you divide by time, and you expect this to be finite when it's diffusive. And
the expectation would be 0.
Otherwise, yes, it would be 0. And it's not the first time I'm presenting that, so well. So when you put the expectation outside and you do this little computation, you see that you end up using stationarity. You end up with this formula, and so when you let time go to infinity, this factor disappears, and here you put plus infinity. So then you realize that this effective diffusion coefficient here is related to the mobility up to this factor beta. So this means that there are two ways of computing this effective diffusion. Either you let the particle diffuse spontaneously and you measure the spontaneous diffusion, or you help the particle to move by applying a constant force and you look at the average velocity this generates. Right, and so that's the kind of things you'd like to compute in practice. Alors, now, again, those are very nice formulas. So maybe this one's a very nice formula, but it's a formula for continuous dynamics. Now, in practice, you want to discretize and make sure that your discretization does not corrupt too much the properties you compute. So there are two things to control. There is a statistical error, which you control as you did before, by doing several independent replicas and estimating the variance. And there is a systematic bias, which is a bit more complicated. So I won't go into the details here, but it's simply to advertise the fact that those kind of continuous integrated autocorrelations can be estimated from numerical simulation with some remainders which are related to how well the invariant measure approximates the Boltzmann-Gibbs measure. And so there are formulas for what are the corrections and so on. And for the scheme I've shown you before, so this Langevin scheme, in fact, here you know that you can have errors of the order of delta t squared. So it's nice to have those kind of formulas because, of course, in practice, you would like to take the time step as large as possible in order to diminish the statistical error and to have a faster convergence. But if by doing so you increase too much the bias, at some point you will lose on the numerical efficiency. So it's really important to understand what kind of errors are there. So that's one. Error estimates when you look at the Green-Kubo formula. For the non-equilibrium dynamics, I would do as before. I would integrate my Langevin dynamics, except that I would replace minus gradient of v by minus gradient of v plus eta f. But otherwise, it's more or less the same scheme as before. And I would define the mobility by looking at the average velocity computed over a very long trajectory. And then, just the take-home message will be that you can characterize the invariant measure for this numerical scheme. It's a perturbation of the Boltzmann-Gibbs measure, which depends on two parameters, the time step delta t and the parameter eta, which determines the strength of your forcing. So you can write a double expansion in eta and delta t. And you can look at the linear response, and this allows you to prove that what you compute, the mobility you compute numerically, is the correct one, plus a perturbation of order delta t to the power alpha, where again alpha is how well you approximate the invariant measure with the scheme when there is no non-equilibrium forcing. And then you can do overdamp limit, superimpose metropolis, blah, blah, blah. I mean, there are all sorts of technical extensions you probably don't want to hear of. But this last extension here, I mean, taking overdamp limit and superimposing metropolis, is in fact what people do in PEXA to compute self-diffusions of ions in clays when they use some effective overdamp Langevin dynamics. So although it's a technical extension, it's something which is relevant for the MOMAS community, or at least a sub-community of MOMAS interested in molecular simulation. And well, this was just to show that, well, it works, which, well, maybe I just comment that. I mean, here I'm showing for a simple 2D potential, when I increase the forcing strength in my Langevin dynamics, what is the average velocity? Just to motivate the fact that it starts off linearly, and at some point, when the forcing is too large, you start to see non-linear effects. So typically, you would take forcing which are sufficiently small, compute a few values, and then look at the slope, and this would give you your mobility coefficient. And so you do that for the various values of delta t, and so you record the slope as a function of delta t, and then you see that as delta t goes to 0, everyone predicts the same values, and then depending on the order of the scheme, you've got variations which may be of order 1 or 2, and 10 if you are very clever, and so on. So this was to motivate that you can compute self-diffusions on a computer, and errors can be controlled. So maybe just one last slide about what I haven't mentioned. So it's nice to mention something. It's also nice to say what I haven't mentioned. And I could spend 10 hours on that, but probably no one would be left in the room. So the things I haven't mentioned, and which you could find if you're interested in the literature, is sampling other ensembles than the canonical one. So especially constant energy ensembles by discretizing the Hamiltonian dynamic. That's very nice to present. It's a very, I mean, it's a very well known theory now. It's a beautiful one. And then extension to other ensembles like a constant pressure. So when the volume is not fixed exactly, but when the volume oscillates in such a manner that the pressure is fixed in average. So pressure here would be understood as the Lagrange multiplier of the volume constraint. So this particularly relevant for biological simulations where you want to fix, well, where pressure, atmospheric pressure is fixed in our bodies rather than the volumes. So another thing is variance reduction techniques to limit the fact that the prefactors in the statistical error are very large and to cope with those metastability issues. So I mean, that's something which is quite understood for equilibrium dynamics. I mean, there are some ways to do it. For non-equilibrium dynamics, it's really, well, it's really not understood, I would say. There is a computation of free energy differences. So I've talked today about computing average property like pressure, but there are properties like free energy, entropy, and so on, which are not the average of something. They are really related to the partition function and not averages of something. And so there are dedicated techniques to compute differences of free energies rather than the free energy itself. And this is important, for instance, to assess the relative likelihood of two typical conformations of a molecule or other systems, or two-phase transitions in a solid. There is also the sampling of reactive trajectories, so trajectories when you see something relevant happening, like a molecule which changes its shape. There is also the coupling of molecular dynamics with either the finest scales, so some quantum mechanical computations in some part of the systems where you have some chemistry happening, because molecular dynamics is nice, but it's for systems which are more or less chemically inert. I mean, you don't see bonds changing all the time in molecular dynamic simulations, except for some very specific potentials. And so if you want to have some chemistry involved, it's useful to potentially couple molecular dynamics with some quantum mechanical computations where you really resolve the status of each electron as to decide whether there is what is the time of bonding interactions. And you want also to couple molecular dynamics with coarser scales like Navier-Stokes ones or maybe DPD ones, which is some mesoscale dynamics, in order to feed some more coarse-grained models which may be relevant at, in regions where the system is at local thermodynamic equilibrium and you would like to focus on some important region where you're out of equilibrium. And the last point, which I don't know much to do about, but I mean that's it's really a huge industry in the applied community, is to develop better potential energy function, because as I've mentioned, most of the error in molecular simulation is the modeling error related in finding the right potential energy function V of Q. So as mathematicians, there's not much we can do about it, so we do about almost everything else. But I mean, there are many people developing better potential energy function, and hopefully there are people doing that because we desperately need them to be more quantitative and more predictable. On that note, I thank you for your attention, and I'm willing to take any questions, but beware, they are recorded.
Thank you. Yeah, about the last part, you say the formula for the diffusive effective coefficient was an average on the initial position too. I mean, it's not only something that you average over time, but also on the average of the initial position. How do you sample them? I mean, what do you do for that?
So typically, I would do an equilibrium Langevin dynamics, which I would subsample, and I would start from all those, and I would start a trajectory from all those conditions. So the initial conditions would not be strictly independent, but they would be well distributed. And if I make sure that I wait sufficiently long between two subsampling time, then they would be almost independent. And the way to quantify that would be to look at the variance and the decay of the variance of the equilibrium Langevin dynamics. And this allows me to know how long points are correlated.
So there are no other kind of heuristics.
I mean, so that's the orthodoxic way, I would say. So the most exact way. In practice, of course, people don't do that. They don't. They wouldn't. Most people don't do that. They would do one very long trajectory, and so they would say that along the trajectory, points are distributed according to the canonical measure, and so they would compute cross correlations along the trajectory. That's another way to do.
I have one more question. So you define an effective diffusion coefficient. How is it related to the, let's say, diffusion coefficient at a macroscopic scale? I mean,
but that's the one. I mean, the one I've shown on the last slides here, the one which is not well defined here, is the one you obtain by homogenization theory. I mean, homogenization of the SDE. When you look at the, maybe let's write it here. When you look at capital Q of t, which would be the integral between 0, the initial position, plus the integral between 0 and t of the velocity, minus ps ds. And so here you don't periodize, meaning that there are little q's, and here my capital Q is when I do not reperiodize, so I let it drift in time. And so when you look at that over diffusively long scale times, like t over epsilon squared, and you rescale by epsilon, so this weakly converges to square root of 2 d dbt, bt, sorry. So it's which means that this converges weakly to an effective Brownian motion whose covariance matrix would be given by d. So that's really the way it works.
Any other questions?
Non, c'est que j'étais.
Yes, I have a question about also the diffusion coefficient, but in porous media. Because you said that it's possible to simulate 10 to the power 6 of molecules or particles. What space size of the sample you can simulate, for example?
So I mean
because in porous media you have the question of the porosity structure. So
I mean it's going to be deceptively small. So if you want, let's say I can simulate 10 to the 9 particles, which is already enormous. So this means that you've got 10 to the 3 per direction. And since the typical length scale is 10 to the minus 10, you see that it's about 10 to the minus 7 in each direction. So let's say a fraction of micrometer. So we can talk about something like a fraction of a micrometer squared, cube, sorry. Like 0.1 to the cube. So I don't know what the size of the pores you have, but probably it's larger than that.
No, in clays, for example, there are typical sizes, pore sizes of the 10 nanometers.
10 nanometers. Oh, okay, so I mean, this is only 10 times larger then.
Yeah. But then you can give a try to calculate the effective diffusion coefficient for some synthetic clay model, maybe. So
what I understand my colleagues at PEXA do is in fact that, I mean, in this situation here, you would be simulating every molecule of water and so on, so everything. And what I understand people do at PEXA is that they use some effective dynamics which is only on the ions which are in solution. So I mean, water is removed from the model and is only taken into account in average through some hydrodynamic model for some multiplicative noise in the Verdun-Langevin equation. And with that, they can go to much larger sizes. But then it's also an effective model of clay in some sense. It's not a clay which is resolved at the atomistic model. So the way they would do is they would do very fine atomistic simulations to estimate the parameters in this mesoscale model, and then they would compute the diffusion of the mesoscale model.
Yes, okay, thank you.
Other questions?
There's also a bunch of accelerated MD techniques out there. Accelerated MD through temperature control or things like that, and I suppose the dynamics are very different. Did you adapt the theory for?
So I mean, what you mentioned by accelerated techniques, I would probably put it here either in variance reduction or sampling of reactive trajectories. So in parallel tempering, for instance, where you do a simulation at a higher temperature so that it's easier to go from one to visit the space, and then you cool it down. I mean, that would typically be something along those lines. In other accelerated techniques where you put some bias on your system, or you simulate many things in parallel and you want to sample trajectories, that would go into this direction.
Thank you.
So it always depends on what is the aim. If the aim is computing an average property, and then all you have to make sure is that your dynamics, even though it's biased, has the correct invariant measure, or you can correct for that. Or if, so that's the simple case. If you want to sample trajectories, then when you bias the dynamics, you bias dynamical properties, and it's trickier to unbias.
Merci.
Okay, so if there is no more question, we will have time for a coffee break. Thank you again.